Hi, and welcome to Dr. V's Chemistry Webcast. Today we're going to talk about how to do calculations when we're keeping track of significant figures because we're using measured quantities. We need to know how to do this properly. So if we're doing calculations where the values going into the calculation are measured quantities and they were reported with significant figures that depend on the nature of the measuring device, we can't get answers that imply that the measuring device had finer markings and smaller divisions than it did. All right. And so we can't have answers that are more reliable, or I should maybe say more precise here than your least precise measurement. All right. You can put numbers into the calculator and the calculator might spit out all kinds of digits after the decimal place. But that doesn't mean that you suddenly had a ruler that was marked to, hundredths of a centimeter. You can't imply that. And so we have to know how to take care of this when we report our calculated values. Okay. So let's talk about how to do this. And what we do depends on the mathematical operations that we're carrying out. So if we're adding or subtracting, there's one set of rules. Okay. So when we're adding or subtracting, we're going to round our answer based on the measurement that has the fewest digits after the decimal place, or with the estimated digit in the highest place. We can't get more precise than that. We can't have more digits in our answer after that place, even if we add or subtract. That implies that our ruler was better than it was. It implies that our balance had smaller divisions than it did. That's just not okay. So let's go through an example here. All right. Object 1 had a mass of 1.23 grams. Now we see that the estimated digits in the hundredths place. And that tells us that the balance we used was marked to every tenth of a gram. Object 2 had a mass of 6.1955 grams. Now, the estimated digit here, right, is in the tenth of a milligram. All right, so a much more precise balance. I have lots more digits after the decimal place. But if I wanted to find the mass of these two objects together, all right, the calculator gives me 7.4255 grams. But this suggests that both measurements, right, had that kind of precision out to a tenth of a milligram, and that's not true. All right, object 1, my estimated digits in the hundredths place. Object 2, of course, has digits farther out than that. But what this means is that I have to round my answer to the hundredths place. Okay, I can't be more precise than the measurement for object 1, where my estimated digits in the hundredths place. I have to round my answer to the hundredths place. So I need to report this total mass, not as 7.4255, but as 7.43 grams. So we have to remember to do this when we're adding or subtracting. It's based on place. Students sometimes really don't like this rule, but it's what we need to do. We can't imply that the measurements had more precision and more significant figures after the decimal place than they really did. That wouldn't be truthful. So we do a different set of rules when we're multiplying or dividing. All right, for multiplying or dividing, we have to round our answer to have the same number of significant figures as the measured quantity with the fewest significant figures. All right, so let's say we measure the length of a rectangle to be 10.41 centimeters. And the height of this rectangle was 5.78 centimeters because it was not very tall. All right, so if we wanted to find the area, all right, area is the length times the height. Okay, we can multiply these two together, and my calculator gives me all kinds of digits. Okay, that's fine. That's what my calculator says. But I can't report my answer like that because that's implying, again, that I have a ruler that was going out, to thousandths of a centimeter. That's just not what we had. It only went to a tenth. So when we're multiplying and dividing, we have to do this based on fewest sig figs. So if I look at the length, that was reported to, that had 4 sig figs. And if I look at the height, it had 3 sig figs. Well, 3 is smaller than 4. So I can only have 3 sig figs in my answer. So I'm going to report it as 60.2 centimeters. Centimeters squared. Wash those units, all right? Centimeters times centimeters gives me centimeters squared. And so we do want to pay attention to that and make sure we have the correct number of sig figs, that our answer makes sense, and that we have appropriate units, and that the units make sense for the problem we were doing. All right, so the rules aren't particularly hard, but I I have noticed in the 20 years I've been teaching chemistry that students forget about the adding, subtracting rules being different from the multiplying, dividing rules. So I'm pointing that out to you so that you don't make that mistake. I don't want you to forget that when you're adding and subtracting, it's about place. Now, there is one other complication that I need to talk to you about. Okay. What if there are multiple steps in the calculation? Well, you have to follow your order of operations. Okay. You have to figure out the answer for each part. And if you do round for intermediate steps, which really I don't recommend, you need to keep at least more than one digit than you need. And you're not going to round for sig figs until the end. So you sort of have to mentally keep track. Okay, I was subtracting here. This is where the place is where I would have to round. And now I have to multiply. And now I have to look at the number of sig figs. And you have to keep that all in your head and not round for sig figs until the very end of your problem is my recommendation. And of course, you're going to include units. All right, so let's go through and do a sample problem, something that you might encounter in chemistry class this year. Calculate the percent error for the measurement of the boiling point of naphthalene, which is used in mothballs. So naphthalene, which is really stinky, has an accepted boiling point of 217.9 degrees Celsius. You measured it in lab and you got an experimental value of 221 degrees Celsius. All right, so we're trying to get a measure of our accuracy. How close were we to the accepted value? Percent error formula, which you should memorize, quite frankly, the accepted value minus the experimental value, take the absolute value of that, divide by the accepted value, and then multiply by 100. Right, we're trying to get a gauge of how far away we were from that accepted value. All right, so let's substitute our answers in. All right, so we accepted minus experimental over the accepted times 100. And what I want to point out, notice that the numerator involves a subtraction step. All right, and subtraction, you have to remember, is based on place. Where's that last estimated digit? And then we divide, and the division step for sig figs, we're thinking about how many sig figs. So we're going to go ahead and complete this, okay? So 221 minus 217.9, that'll give me a numerator, and I divide by the accepted value. So I get 3.1 divided by 217.9. But I had to be careful here. My calculator gave me 3.1. But I know that for that subtraction, okay, 221, my experimental value, that estimated digit's in the ones place. I have to round that difference to the ones place. So I wrote down 3.1, but I have to remember that I really only know it to the ones place, so it's 3. But I don't want to put that in yet because it might distort my answer. So I'm going to leave it as 3.1, but I know I really only know it to the ones place, which means I really only have one sig fig there. And then I'm going to divide it by the experimental value. And then, all right, I know I had to multiply by 100. So what I have to remember is that, okay, when I do 3.1 divided by 217.9, all right, my calculator gave me several digits. But I only know it to one sig fig because it's right from the subtraction piece. And then I'm going to multiply it by 100. Now, another thing that sometimes trips students up, what students sometimes forget, is that 100 is a pure number, right? It's an exact number. It's not a measurement. It's literally just the formula to make it a percent, right? It's not a measured quantity. It has infinite sig figs. It's not going to affect my rounding. It's the fact that when I subtracted the experimental value from the accepted value, that I only knew that to the ones place means I only know my percent error to one sig fig. So I'm going to report my answer as 1% error, which is pretty good, right? We're going to be happy with that. So we're going to stop here, all right, and that's good.